Hello, welcome to the section 1.5 pre-class video assignment. So in this video assignment, we are going to be looking at solving something called the linear first order equation. So still first order equations. Now we're going to be looking at a particular type that's known as a linear first order equation. So here is sort of the definition of a linear equation. It is something that looks like this. So first order, because there's only a dy dx present, no higher than that derivatives. But what makes this linear is that, in fact, the dy dx appears only to the first power, and the y, so this unknown function y and its derivative dy dx, these unknowns appear to the first power only. So that is what makes this linear. Just think of it in terms of a regular old algebra equation. If you had something like 2x plus 4 equals 11, this is clearly a linear equation. What makes it linear is that the unknown x appears only to the first power. So we have the same situation here. In a differential equation, it is linear if the unknown function y and its unknown derivatives appear only to the first power. So a couple of examples here to look at. So in the first one here, we are deciding whether the following DEs are separable, linear, both, or neither. So separable, we talked about in the last section. There's a bit of discussion about that here. I will leave that for you to read. So let's concentrate more on whether this is linear or not. So what's important here is that the unknown here is our function y and its derivative dy dt. And here we can see that indeed the y appears to the first power only, and the y dy dt appears to the first power only. So this is in fact a linear DE. Note that, yes, e to the t, ln of t from an algebra perspective are not linear, but we don't care about the t. T is only the independent variable here. It is not the unknown function. So you don't actually care whether those appear linear or not, only the y and its derivative dy dt. So the only other issue then is just recognizing what is the unknown function here. So a couple of examples. In the next DE, we can see, again, here's Leibniz notation is fairly helpful here. Dx dt is telling us that t is the independent variable, x is the name of the unknown function. So I can see that dx dt appears to the first power. There's an x here that only appears to the first power. However, there is an e to the x. E to the x. X is the name of our unknown function, hence e to the x is not linear. So this DE would not be linear. All right, so give this a go on my open math. And again, one more example here. Again, this is generally not a difficult topic, but it can be confusing with lots of letters and different things flown around. And again, this is a place where Leibniz notation is actually helpful. In the next DE, we see we have a dr d theta. That means that r is the name of the unknown function. Theta is just an independent variable. So I need r to be to the first power only. I need dr d theta to be the first power only. The only other thing here is a theta cubed. That is not linear, but it is not about r, so we don't care. So this one is linear. This is a linear DE. All right, so here's some more to try on my open math. All right, so let's talk about the method then of the section, what we are trying to look for here. So the method here is using something we call integrating factors. But underlying the whole method is the following. If we are very, very lucky in our DE, and our DE just happens to look like this, then we're in business as far as solving this thing. If this thing on the left-hand side of our DE is really just the result of a product rule derivative, which this is, then we have a fairly quick and easy way to solve. So notice this is a1 of x times the derivative of y plus the derivative of a1 times y. This is the product rule. If you undo it, this expression on the left-hand side is the derivative of y times a1, or a1 times y. So a solution then can be obtained by integrating. So here's a little true-false question on my open math about the product rule that pertains to this question. Give that a go. Again, if we spot this situation, then we can see that we can just solve by integrating on both sides. On the left-hand side, we're integrating the result of a product rule derivative. And again, this is integrating the derivative of y times a1. Integrating and differentiating are reverse operations of each other, or inverse operations of each other. So you just end up with y times a1 of x. And then the problem just comes down to integrating the g on the other side. If you can integrate the g to get big G, of course, we have a constant of integration generated, we can solve for y of x fairly easily. So this is the idea of the underlying concept of the method. Now, of course, in general, we aren't so lucky to always just have a product rule sitting there. But what happens here is that we might, in this method, be able to figure out a so-called integrating factor, which is usually called mu of x. And by multiplying through our dE, we can create the product rule situation that we saw above. So let's take a look at this situation. Basically here, to make this work out, we first write our dE in something called standard form. So basically, it takes our original dE at the top of the first page there. We divide everything through by a1 of x. Then I basically have a function in front of the y here, and then another function on the other side of the equal sign. So these are just functions of x. We will now call those p and f. And so this is basically our standard form, where we have dy dx plus p of x, some function of x times y, equals a function of x. So we want to, this is where these questions will start. We start by converting whatever our dE is into its standard form. So this is something a little to practice on. All right, so let's suppose we have this integrating factor. Let's suppose we have found it. We'll talk about where it comes from later. But if you multiply it through on both sides, we would get something that looks like this. So we take our standard form, we multiply it through by this integrating factor, and then let's just suppose that this was the correct integrating factor to create a product rule on the left-hand side. Then what would that product rule look like? That product rule would look like this, basically. It would be the derivative of u of x times y equals mu of x times f of x. So this can then be solved, as we saw before, by just integrating on both sides. So as long as we can integrate mu of x times f of x, we can solve this for y and get a solution this way. So again, we take this integrating factor, we multiply it through our dE, and this integrating factor needs to be chosen in such a way as to create this product rule situation that we need. So the question is, of course, how do we choose this integrating factor to work this way? And basically, let's just think about what would have to be true for this to be the case. So if we look at our left-hand side, where we multiply by the integrating factor, this is what we have. We've got the dy dx and the y, so the rest of it has to be, well, this is my mu, this has to be mu prime. So for this to be the product rule, this is mu of x. This guy right here in front of the y has to be equal to mu prime of x. So that means this is what has to be true in order for this mu of x to be an integrating factor. But that is just a differential equation to solve, so that's kind of ironic. This is just solving a differential equation in order to find this mu of x. This differential equation happens to be separable. So if you look at this as being d mu dx is mu times p, then we can again separate it and we can integrate on both sides. And we end up getting this solution that we have ln of absolute value of mu is the antiderivative of p of x dx plus a constant. So we can solve this for mu, take e on both sides. Again, the plus c is like saying e to the c, so we can move that in front as a k, and this is basically what we get. So this is a good start. The nice thing here is we do not need a particular integrating factor here. We just need an integrating factor. So the good idea here is to choose something nice and easy. So that is, let's not worry about whether this is negative or not. Just get rid of the absolute value. Let k be equal to 1. This is a convenient integrating factor to use. We don't have to make it harder and more complicated on ourselves by picking a more complicated integrating factor. We just need an integrating factor. So this is the convenient one to use. Mu of x is e to the integral of p of x dx. Again, where does that p of x come from? In standard form, the p of x is this guy right here. Yes, this guy in front of the y. This is our p of x, and that is how we choose our integrating factor. All right, so give it a go. So this is the formula. Jot this down real quick. This is what you need in order to come up with a mu of x. So give this a try. And then there's another multiple choice to try this on. All right, so let's just try one before we leave this packet. Well, let's try one from beginning to end. Fairly easy one. Let's see how the method works. So here is the idea here is to solve the DE. We are to give the largest interval over which the solution is defined and determine if there are any transient terms. So we can talk about that later. Basically, this is our fairly simple DE to start with. So the first thing we do is we write it in standard form. In this case, that's fairly easy. We just move the 2y to the other side. And then we can see that the p of x function here is just the function, the constant function -2. So from this, we can come up with our integrating factor. The integrating factor will be e to the integral of -2 dx, and that is, of course, e to the -2x. This is our integrating factor. So we multiply the dE all the way through by our integrating factor, including on the right-hand side. And then what happens here is that this thing on the left-hand side will be in the form of the product rule. You can see it. We have over here an e to the -2x, and over here we have its derivative, -2 e to the -2x. So this is a product rule situation. In fact, the product rule would have been d dx of e to the -2xy. So d dx e to the -2xy equals 4 to the e to the -2x. Integrate on both sides. We get e to the -2xy equals, again, this one's a fairly easily integrable, or it's a little u sub. Don't forget the plus c, and then we can solve for y. Once we have it solved for y, you can clean it up a little bit. Like I can divide both by e to the -2x. Again, remember exponent notation. This would be -2 times c e to the 2x. And again, we see that the constant of integration is important. It's not just a plus c on the end anymore. It is now kind of worked into the function itself. So that is important. Again, quickly then, the largest interval here, there are no domain issues here. So the largest interval is the entire real number line. A transient term is a term that goes to 0 as x goes to infinity. It's a term that disappears. So that is a bit of a moot point here. There are no transient terms here. -2 does not go to 0. E to the 2x does not go to 0 as x goes to infinity, so there are no transient terms here. And so that's just a fairly basic example to work through. We will look through some harder examples as we work through the notes here. The somewhat good news here is the only really tricky thing here is it can be a little bit difficult depending on the integrals that you run into when you integrate both sides. The part of setting up the product rule can be fairly routine. Again, just as long as you're okay with integrating and finding your integrating factor, the process here is fairly routine, and then it really just becomes a matter of how hard is it to integrate on the right hand side. One little example then before we go, on my open math, there is one integral you're going to practice on. It is a scaffolded problem on my open math, so you will be stepped through the problem. This is a calc 2 type integral that can be a bit tricky, but it's basically a substitution that leads to a by parts type problem. So give that a go on my open math. We will run into an integral like this during the section. And that's basically will be it for the video assignment today. We will finish up the rest of the packet together in class. Thank you.